This talk will be about work that is more or less the last experimental work that was carried out at my lab at Harvard. It's a collaboration with two materials growers, the Niels Bohr team run by Jesper Nygaard and the Luden team run by Hong-Ki Su. And these were the experimentalists who were participating, graduate students and postdocs. And I have three things to say today. The first is about the zero bias peaks and their relationship to Andreev bound states. This is something related to the work that you've seen with Leo's talks and our own efforts to both reproduce that and extend it in new directions. The second is oscillatory splittings. You've already heard about this, this multiply smoking gun story that Shankar wrote a paper about and that Leo showed some data about also. The third aspect of this talk has to do with what do we do next. So it's clear that, in my opinion anyway, we've come a long way, but we haven't finished the problem off yet. And so I think that one of the things that we have to talk about now at this point in the session is what do we do next? And so that will be the last part of the talk. So these are experiments that to a large extent were motivated by the Delft work, and one of the things that we wanted to do first was just to see whether or not we could reproduce it. I think that that's an important thing to do when an important experiment comes out, is just see if it was an artifact, see whether or not it only happened once and it only happened in that lab. So the wires that we have studied are very similar, indium antimonide wires with a normal end with gates underneath an oxide and a superconducting contact. There were also two-sided devices that we'll be talking about also, and these are 111 grown indium antimonide nanowires. Again, this particular experiment was grown in the lab of Hong-Ki Su, and I thank him for providing those wires for this collaboration. So this is a data set which the color's not fantastic, but what you can see is a superconducting gap, a rather soft gap that as the magnetic field is turned up produces a zero bias peak. If you like this kind of plot better, you can see here a relatively soft gap that turns into a zero bias peak as the magnetic field is turned up. So the first statement to make is if you were worried, you might not have been, but if you were worried whether or not the data that you've been seeing so far is a one-off experimental result, it's not. It's at least a three-off experimental result. It might still be an artifact, but it seems to happen at least all over the world, and every time you try to do it, you get results that look like this. But something's interesting about this data, which is that the conductance is quite high. This is not taken in the tunneling regime, so the notion that this is a spectroscopic measurement of a state that lives at the end of the wire has to be expanded a little bit to think about an actual conduction measurement at high conductance. We can change the conductance down to the kinds of values that you've seen before, down in the low, but below, order 1e squared over h. And when you do that, okay, this data doesn't happen to be so pretty, but you can see the similar thing happens. You have a kind of a soft gap, and as the gap goes up, a zero bias peak appears. So far, so good. If you move to higher conductance, all kinds of things happen. In this case, a relatively soft gap, and then a very strong zero bias peak. Now, I wish I could tell you what were the conditions under which a zero bias peak would be very strong or very weak. I don't know. These were at different backgate voltages and different devices, and there was a lot of variation in how these things performed. The general phenomenology was common, but sometimes they looked like this and they were fantastically strong and unsplit, and other times they weren't. So we're still on the learning curve, and we're still trying to understand how and when and why these things appear. If you constrain the device with a couple of gates, this is now the normal superconductor interface, there's the wire underneath, and you energize a couple of gates, you can even produce Andreev bound states. That is, instead of seeing a soft gap, you can see resonance states. In this case, the resonance state between the barrier and the superconductor, it appears to us, produce these oscillating states that change as a function of gate voltage. And if you sit at one line, here shown by the red line, you can see that at zero magnetic field, those two Andreev bound states correspond to those two peaks. And so the simple picture that Shankar talked about, that he would have liked us to have seen two simple peaks coming together and producing a Majorana out the other side, may be more readily observed in this kind of a system. You can see here the color's not, I mean, it's black and white, but it's a little bit hard to see. But here are those two peaks, and here they move together with roughly the Zeeman splitting of indium antimonide. I've taken a derivative of these things so that you can see where the peaks live. This is a second derivative so that a peak looks like a dark spot. It's a maximum, so it's a negative of the second derivative. That's why it's low. It's the second derivative. But you can see, if I help you, you can see that these two peaks come together, and what appears is that three peaks come out of the middle. And this was really the kind of signature that we were hoping to see. And when, in our case, when we have these Andreev bound states present, it appears that they happen in a way that's easy to see. So what's all the fuss about? Maybe we can just declare victory over this straightforward particle physics discovery on a solid state system and all go home. It's more complicated than that, because as was emphasized in the previous talks, there are zero bias peaks that appear for other reasons, and one has to tease apart the origins of these zero bias peaks. Here, for instance, is an experiment from DeFranceschi's group in which a superconducting wire lives between, in this case, a indium arsenide wire lives between two superconductors, forming effectively a quantum dot. The quantum dot has at low and zero magnetic field some superconducting density of states, which when you turn up the magnetic field produces this extremely strong zero bias peak that appears at finite magnetic field. We ourselves have recently published a paper in which a slightly more complicated device, now two superconductors. This device happens to have the two superconductors wrapped back around each other and connected via a ring so that you could change the relative phase on the two superconductors. But it's just one more knob on the experiment. But again, two superconductors, and here a weak probe with a gold contact allowing a spectroscopic density of states. You see these Andreev bound states. You can control where the Andreev bound states are by changing the phase on the two superconductors by threading flux through them. And when those two Andreev bound states that are evident here are put in a magnetic field goes up, and a gigantic zero bias peak appears that was not there at low field. You can even see that zero bias peak, if I zoom in on this region around 16 to 18 Tesla, shows evidence of superconductivity. It's still phase dependent. So it's not right to say that it's just a Kondo peak that has appeared and it doesn't have anything to do with superconductivity. It itself is blinking on and off with the phase on the superconductors. So there's some mix of states. Now we are at sufficiently low magnetic field that unless these states came down, I mean, this is the mechanism that Modi talked about in his talk. He said, you know, if the criterion is to have the Zeeman splitting larger than the gap, that can happen two ways. One, the gap can get smaller, and two, the Zeeman field can go out. But these are rather low magnetic fields. This is 10 millitesla. It's rather hard to imagine that the Zeeman splitting has increased to the point that this has collapsed and then the peak has come up, although these do look like they're going down. It's not the case that this gap has collapsed and something has come up. Rather, this looks like dot physics, and the way I can support that is by saying, if I take this system normal by applying only 30 millitesla, which drives the aluminum normal in this case, I can see very clear even-odd structure, even, odd, even, odd, because it's a Kondo, non-Kondo, Kondo, non-Kondo valley. If I look at the corresponding superconducting states, I see pi junctions that exist down here. If I look in these pi junction states, these are the ones that produce the Kondo peak. You shouldn't be surprised because that was the setup. I designed it to make a Kondo peak. I set it up so that I knew that it was going to be a Kondo non-superconducting system at high field. So this was kind of a setup. But it's interesting to ask, how is this related to the kinds of experiments you've been hearing about during this session? Why should I be talking about quantum dots when nobody's making quantum dots? We're putting up barriers. The answer is that a barrier is actually a very complicated object, unfortunately. Everybody thought a barrier, you just put up a gate voltage and you make a constriction and you tunnel through it. But the physics of a quantum point contact is actually a spinful, interesting problem in which additional states form even at zero magnetic field, as if the role of interactions in a constriction is to create something which has an extreme sensitivity to low magnetic fields, as if the system were a paramagnetic state ready to be polarized at low magnetic field, and effectively a divergence of the susceptibility, just due to interactions. So, does that drive the Zeeman field at which these systems can become Majorana-like? The effective Zeeman splitting in the vicinity of a constriction can become larger by virtue of interactions instead of straight Zeeman physics? Maybe. The fact that a constriction itself is a spinful object makes this complicated. One solution you may turn to is to say, well, if even just a constriction is too complicated to figure out what's going on, maybe I should make some object which is surely not a spinful object, surely incapable of showing the Kondo effect. So I could get Kondo off the table and not worry about it. Well, one way you could do that would be to explicitly make a quantum dot. And if you make a quantum dot in which you have an odd occupancy, don't look at that one. Look at the next one, because that one is an even occupancy and will have zero spin. So in fact, if I look at slice number one, if I do what I just said not to do, if I look at slice number one, I see there's a zero bias peak. It's a little hard to see in this light, but there you can see a kind of zero bias peak as a function of gate voltage at zero bias. And if I look down here, you can see that that is indeed a Kondo peak. How do I know? Because that thing splits with a large Zeeman splitting, the Zeeman splitting of indium antimonide. But it's a little hard to see, but it leaves behind something that doesn't split. So there's the confusion in a nutshell. I take a system which has Kondo physics in proximity to a superconductor, I split the Kondo peak, and a third peak remains, which is evidently unrelated to the Kondo peak. So good, let's get rid of the Kondo peak by going to the next one over, number 2. Now I only have still a zero bias peak, presumably with no Kondo, and it doesn't split. You add a magnetic field, and it stays right there at 0. So is that a way of getting the confusing aspect of the constriction, which itself might be capable of Kondo physics, out of the problem? Perhaps. And perhaps that's the peak, and not that thing which has all elements wrapped up in one. That was the first part of my talk about interactions. The second part of my talk is about the splitting. You've seen this paper several times now. There's smoking gun evidence for the existence, and here are the oscillations that we should be looking for. Here's the experimental data in which very many times, and I wish I could tell you when it happened and when it didn't happen, but very many times the peaks close, then they split. The peaks close, then they split. They even look a little bit like they come back together there. And if you study this with niobium tinitride, which is what this superconductor is, they'll stay superconducting up for a long time. And so you can see this first peak, and it kind of splits, and it comes back together, and it splits again, and comes back together. And then it's kind of a mess in here. You can't see really what's going on. And then it looks like it comes together, and then it splits, and then it comes together, and then it splits, etc. So it really does look like something oscillatory is going on. And if you remove some smooth background, you can see it a little bit more clearly. And you can look at slices of this, and they look oscillatory. But if you go to be quantitative about this splitting, it gets kind of complicated. And here an analysis from Daniel Loss's group shows that the peak splitting, and this is the same in all of the other papers as well, the zero bias peak which splits and comes back together and splits and comes back together by the mechanism that Shankar mentioned, this RKKY-like interaction, has as its own signature that the spacing between peaks is not evenly spaced in magnetic field. You can see the peaks are getting farther and farther away from each other, such that the nth peak meets at a magnetic field that grows like n squared, not like n. If it was n, that would be linear, splitting. But it grows like n squared. It gets bigger every time. So when we look at our peak splitting by taking that cut of the second derivative down the middle, we see the oscillations of the peak splitting. And if we go find the nth peak, we see that the position of the nth peak does not scale like n squared, but rather scales like n. So Is that a Majorana test that fails? I mean, there are peaks, and they do split, and they do come back together and split and come back together, but they don't have this particular spacing. Or is it that we need a more careful model of this splitting function, which itself needs to take interactions into account to understand how splitting could occur? It's important to say that this is not just a failure of a prediction. This is the verification of something which has yet to be predicted. Okay? So, I mean, it's not like the points are all over the place and you had a line and it didn't go on the line. It's clearly doing something. It's just that the something hasn't been proposed theoretically yet. Okay? So, get to work. Now, the last part of my talk is about the future. We need to imagine that the theorists who have gotten very far ahead in telling us about all the fantastic machines that we can make are drawing pictures. You know, they have software that makes it almost, they're even better than the real devices at this point. We have to now take these kinds of nanowires and put all kinds of depletion gates and superconducting gates, et cetera. And if we do that, then we get to the point that Leo mentioned in his talk. If you really want to know whether it's a non-abelian excitation, then make it do non-abelian stuff. Make it braid. That's, at the end of the day, the only way to know that you have a non-abelian particle is to make it do something non-abelian. So the first important thing to do is to see whether you can make multiple contacts onto a superconducting, onto a nanowire. Here are a bunch of superconducting contacts, angle evaporated, so opposite in the shadow of the wire produces a gate. And here we can see between a pair of them, this left pair, an interesting phenomenon, which is the magnetic field dependence of the superconducting gap. So here you can see the critical current. This one's mislabeled, sorry, let's say DC current, DC current. That one should also say DC current. And you can see that these last up to about 100 millitesla before they go normal. This is an indium arsenide nanowire with aluminum. So it's maybe not surprising that the magnetic field is so dependent. But this is the point that I wanted to emphasize, and I'll show you better on the next view graph. I'll show you here. There's a non-monotonic evolution of the superconducting state, which means that, contrary to your normal intuition, you can increase the critical current in this device by adding a magnetic field. Now, this isn't the first time that that's been seen here. I was going to show you this paper, Stabilization of Superconductivity by Magnetic Field in Out-of-Equilibrium Nanowires. And you see here that you can, for instance, add a magnetic field and the system goes to zero resistance state at finite field. And this is what we're seeing in the device for a particular magnetic field direction. And you could ask what's going on. Well, there are different papers in the literature with different theoretical models of what's going on. For this particular one, which seems the best suited for what we're seeing, I'll say this, take this paragraph straight from the paper. With all of this in mind, a qualitative scenario can be constructed. Increasing the current results in phase slip generation, which broadens the resistive transition. When a magnetic field is applied, quasiparticles are produced in the electrodes. These quasiparticles dampen the phase slips. So we have this soft gap problem, and when we add a magnetic field, the soft gap problem gets worse. But the soft gap problem, in fact, helps, in this case, to damp phase slips. So that's interesting, and I'm not sure what it's good for, but it's at least a new result associated with superconductivity in nanowires. Last topic for new things to do is in the materials science domain. Here's a nanowire with the superconductor grown epitaxially in the MBE system onto the indium arsenide nanowire. So you can see how it's grown here. You can even directionally apply the aluminum so that only one side of the nanowire gets epitaxial aluminum grown onto the side of the wire. So you can have superconductivity epitaxially connected. If you don't do that, you get this interface layer. This is when you have taken it out and subsequently evaporated aluminum on. You have this interface layer, but not so when you do it epitaxially. And that may be the solution. Here again, an interesting result is obtained. If you go back in the literature, you can see that if you wrap a superconductor around a wire and you put a magnetic field through the axis, that you get a kind of a little Parks effect in which the superconductivity is destroyed when a half a flux quantum threads the wire. And this was something that was well studied in this paper and in others in the literature. And in this case, you can see that you can destroy superconductivity but bring it back to life. In the case of ours, it's quite hard to see, but that's okay. Because the aluminum in this particular wire was extremely thin, the axial magnetic field doesn't destroy superconductivity until well above a Tesla. So we have the prospect of, even though at pi and 3 pi and 5 pi, superconductivity is temporarily interrupted at base temperature, you can drive the magnetic field all the way up to 1.2 Tesla in aluminum in this epitaxial wire and still have the system be a zero resistance state, which is a very interesting thing. And it may be also interesting to ask, what happens when the superconductivity has a twist in it? This one flux quantum threading that makes a kind of Mobius strip of the phase around the thing, does that have any implications? Is the physics of topological Majorana systems the same whether there's a twist or not a twist in the wave function that goes around in an axial direction? So let me review. I covered 3 topics. I covered the role of interactions and how interactions can produce dot physics even when you don't want them, and how interactions can enhance Zeeman-like splitting in a way that could drive to low field, possibly, the appearance of these effects. The second part of the talk was, let's see, can I remember, what did I cover second? Yeah, that's right. I covered, thank you, Shankar. I covered oscillations, and it was complicated because we had a result. It wasn't the predicted result, but let's say maybe there'll be a post-dicted result. And the post-dicted result will show this linear dependence on spacing. Maybe Shankar's already constructed the post-result. Yeah? Yes, yes, yes. That was the point. There's a point I made. Let me emphasize the point again. Yeah, that's right. So the author of the theory refers to it as a Mickey Mouse theory and says that we need a more sophisticated theory, which now may be guided by experiment. Okay. Well, now we have an experimental result. We can see whether or not a theory will agree with it. Forget the experimental result now that you go to develop the theory. And the third new result had to do with new materials, new systems, new directions, and the future of this field, which I hope I've conveyed is far from over. Thank you.
Thank you very much.